Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, so I was slowly bringing into you these formal notations which you may see in any books on quantum mechanics. So you should at least be familiar, even if you don't know the formal group theory, at least in the context of quantum mechanics. Okay. So today the focus will be on groups. We discussed this in the last lecture explicitly on rotations. So for completeness, I am going to go through it again. S corresponds to proper rotation or determinant of the set of matrices which are 3×3 matrices. They have to be orthogonal. O is orthogonal. S is for determinant being 1 or proper rotation and in the 3-dimensional space. SO4 means determinant 1. You can assume that there is a fictitious 4th spatial coordinate even though you don't see it. So it is still research wise we still feel that we may not be in 3 spatial, we may have higher spatial dimensions. Okay. So just keep this in mind. As a mathematics problem you can still put one more extra spatial coordinate. You can treat it to be an abstract coordinate which you don't see, you only see x, y, z. But you can still do the set of orthogonal matrices with determinant +1 and study that collection which you call that group. It forms a group which is called SO4. I am not really telling you the axioms of a group, when does the set become a group. You have to give an operation. Typically since we are looking at matrices, they are matrix multiplications and you need to say in that set every element should have an inverse. If you take the product by the group operation which is matrix multiplication, you should get an identity matrix in the set. So there is a set of axioms which I am not putting in because this is not really a group theory course, but you can go and look it up. Okay. Further, we do study in quantum mechanics unitary operators and unitary matrices, and if you look at unitary matrices which are 2×2 matrices with determinant +1, that collection of 2×2 unitary matrices with determinant +1, so that will belong to a group which is SU2 in the context of rotations. Especially the 2×2 matrices are required for spin half particle, right. Spin half has 2 states possible. So you can write matrix representation in a 2-dimensional linear vector space as a 2×2 matrices. And what are those 2×2 matrices which you have been looking at? It is an exponential of Pauli matrices. Okay. So this is what you have been seeing. So I am just putting it compactly here so that you get a feel of various jargons. When you open a book you may see things. As he pointed it out, rotation in 3 dimension, if you take a vector with the tip of the vector to be on the surface of an orange, if you do a rotation, the tip of the vector will always be on the surface of the orange. Okay. So you can say that the symmetry on the surface of a sphere is SO3, the group symmetry. Okay. It takes you a one vector r vector to r prime, but the magnitude of r and r prime are same. So let me recap what we did for angular momentum before we get to see the groups. So this is what we derived in the last lecture using Schwinger oscillator approach, right. So one of the ways in which you can remember that this is correct is that if the m was this small j, then this is non-zero. If m is minus j, then it has to become 0. So there should be a coefficient with j plus m. Okay, this is one way of remembering it. You can also derive it. So it is a ladder operator again or a lowering operator which takes the magnetic quantum number, reduces it by 1 unit. Similarly, J plus raises it by 1 unit, and beyond m equal to j it has to be 0, which means you will have a j minus m, which will take care of it becoming 0. We derived these things, I am just recapping. And they are simultaneous eigenstates of jz and j squared, sometimes we call it as j3. So this is eigenvalues mh cross and j into j plus 1 h cross 1. What was the angular momentum algebra involving these non-Hermitian? J plus Hermitian conjugate of this is j minus. You can write the algebra, the commutator algebra involving j3, j plus and j minus, and amongst them they satisfy this problem. So that's what is called as the angular momentum algebra. And then we also saw that whenever you have a continuous symmetry like translations, space translation, time translations or rotation, we have a conserved quantity, and that conserved quantity is what we called it as, it comes under the heading of Nether's theorem in classical mechanics, which also goes through for quantum mechanics, but on the matrix elements or expectation values, or in the Heisenberg pictures on the time evolutions of the operator, they satisfy this, right? I am just trying to connect with what all you know so far. So just put it as a table here. What is the symmetry? There is a translation which takes a vector r by a units. What performs this translation? The operator which helps you to perform this operation is the momentum, linear momentum operator, and the corresponding parameter which shows up in translation is the a vector. So the linear momentum has 3, it's called generator, which performs this translation. Px, Py, Pz, there are 3 generators for translation. Correspondingly, there will be 3 parameters which you can call it as Ax, Ay and Az. So always you will see whenever you find the number of generators, you will have equal number of parameters. It won't be different. Time translation is just shift the time by a constant. Nothing happens. Most of the systems which you are considering as Hamiltonian is independent of time. So this is the generator of time translation, and the corresponding parameter is C, which is also one parameter, one operator and one parameter. The last one in this context, rotation, takes an r vector to an r prime vector, r vector to r prime vector. Let us rotate by an angle whose magnitude is theta about a unit vector direction n hat. So you can call theta vector as mod theta times hat n. So this rotation matrix is a 3 cross 3 matrix which operates on this r vector. So what were the generators of this? The generators of this rotation operation, it can be implemented by angular momentum. I will go through those steps also again. And the corresponding parameters. So there are 3 angular momentum components. There will be 3 angle of rotation depending on whether you rotate about x axis, you call it as theta x, about y axis you call it as theta y, and about z axis you call it as theta z. So you see from this neat table for the simple continuous symmetry, and these generators are the conserved quantities. So d by dt of the p operator as a function of t in the Heisenberg picture will always be 0, or equivalently the Hamiltonian for a system which possesses translation symmetry should commute with the generator by the Heisenberg's equation, evolution equation. Is that correct? So everything falls in place. So what is SO3? SO3 is a set of all 3 cross 3 orthogonal matrices which includes the inverse. So the inverse of the R matrix is nothing but, suppose you take theta to be about one particular axis, you just change the sense of rotation to minus theta and they will be inverses of each other. Why? When you take the product of this with this, it will be an identity operation. So representing proper rotation, determinant R is plus 1, that forms a group SO3 under matrix multiplication. You have to give an operation. So here the operation for the group is matrix multiplication. Just giving the set of R matrices or set of matrices which are orthogonal is not enough. You have to give the group operation, and the group operation is just multiplications of matrices. And they are proper rotation, that is why the determinant R is +1. So, such a group is called SO3. You can take an arbitrary axis and look at an angle which is infinitesimal, whose magnitude is epsilon. You can write this n hat times epsilon as epsilon x Ex, epsilon y Ey plus epsilon z Ez, and you can write compactly for an infinitesimal in the sense that I do not want to keep anything higher than epsilon order. I do not want to keep epsilon squared, epsilon z, epsilon x. I do not want to keep anything higher because they are already very small. Keeping only linear terms in epsilon, this is the most compact matrix you can write. Suppose you take hat n to be along x axis, okay, if you take hat n to be along x axis, the one which will show up is the rotation which is epsilon x and epsilon x, right, and I am keeping terms, we will see why I am keeping terms up to epsilon squared later. If you want to keep terms up to epsilon squared, then you can write about the x axis in this fashion. Please verify this, okay. Similarly, for the y-axis rotation matrix, you will have terms in the first and the third column and the first and the third row to be altered, and you have this up to order epsilon. Will these two commute? They do not commute. For infinitesimal, they can be approximated because, but if you want to keep up to order epsilon squared, you will see that it will not commute. Work out this commutator of these two, product of these two, okay. Please do this. Take R x hat epsilon and R y hat epsilon minus R y hat epsilon and R x hat epsilon. Please do that, okay, and see what is that non-zero quantity and write down on the right hand side. Okay, I will leave it to you to do this. If you do that, you will find that the right hand side is this matrix, and if you compare rotation of z of epsilon, if you compare this with this, you can say that it is a rotation about z axis by angle epsilon squared, okay. Just check this. Minus, you remove the diagonal element, so minus the identity. So, this is just to indicate that the matrices of SO3, they do not commute. This is non-zero, right hand side is non-zero. They do not commute if you keep up to order epsilon squared, and the commutator has a unique form. In fact, we will see from here that the generators which are responsible for rotations are the angular momentum, and you can show that the angular momentum commutator algebra exactly reproduces this relation. What is the commutator relation? Lx Ly has to be IH cross Lz, and you can get that out of this. So, rotations in classical mechanics versus quantum mechanics. So, typically in classical mechanics, when you rotate by an angle d omega about an axis perpendicular to the plane, transform the vector r to r plus dr, this is what you do, where the change in vector for infinitesimal rotation, you can write it as a vector product. So that you can write r prime as r times r vector, and you can write that as a d omega cross r. This is exactly what we did in the earlier slide, writing the explicit matrix form, but you can rewrite it in this fashion. This I am assuming you know from classical mechanics. In quantum mechanics, what do we want to do? We want to write a unitary operator for rotation for an angle theta. The subscript is for rotation, corresponding to a rotation r in physical space, which when acts on a state psi, takes it to a new state psi prime. So, you have a state psi, you do a rotation, and that is performed by ur of theta, and that gives you a psi prime, okay. How will I write this? Psi prime as ur of theta on psi. Okay, so there is a unitary operator which can rotate the state and give me a new state. Similarly, I could also write r prime to be in the position basis, which is u dagger of theta. So what will r prime psi prime be? So what is this? It is psi prime of r prime equal to psi of r. So you can try to shift what is happening to psi prime by writing psi prime of r to be psi of r inverse. You can write this to be the, you can invert the transformation, right? You have this as r times r. You can put an r inverse here and write this. Call r times r as r. If that is the case, then r will become r inverse. Then what can you do here? We know what is r on r, that is r prime, which is 1 plus d omega cross r or r times d omega cross r, right? So what will be r inverse? What is r inverse? Inverse will change the angle by opposite direction, the negative sign. So this will become, so what do we have? Psi prime of r vector is psi of r inverse r. I can write this as psi of r vector minus d omega cross r for infinitesimal rotation. Can you do a Taylor series expansion here? It be psi of r minus d omega something wrong here. Psi of r, then can you do this Taylor series expansion and see whether you get psi of r? Have I done it correctly? Yeah, I have done it correctly. So then it will be, this is the correction, this is the correction, so that will be there dotted with del of psi. Okay, so this is a mistake I did. So this is r plus some correction and that correction. Now what do we do? What is the next step? In quantum mechanics, what do we have to do? The del operator has to be converted to a momentum operator. Put I, H cross, convert it into momentum operator, and it's a scalar triple product. Play around and see what you get. Can you check it? What do we get? You roughly know it should be the generator of rotation, which has to be angular momentum. Okay, so let me just go through the summary here, and then in case you have not done it, you can take it from here. So this changes the wave function, which was initially psi of r to psi prime of r. If psi is a scalar on rotation, this is what I said, psi r vector is same as psi prime r prime, and you could rewrite this as psi of r, which can be rewritten in terms of rotation by an opposite angle in the opposite direction. So this is what I did. This is r inverse, and do a Taylor series expansion, which I did already for you, and take I minus IH cross as a momentum operator and rewrite the above. This is what I left it for you. What will that be? There are these in between steps. You can take the scalar triple product, write it as d omega dotted with r cross p. R cross p is the angular momentum, orbital angular momentum. Physical rotations, when you do in physical space, what you have is only orbital angular momentum, and you get automatically the change in psi prime at the position R. So this only gives you the unitary operator which takes psi to psi prime at the same position R. Wave function changes at a position R to psi prime, and how it changes is the unitary operator, and this is unitary for an infinitesimal angle. If you make the angle to be, if you increase the angle, finite angle, then what do you have to do? Keep taking more pieces. You can multiply this thing because it's a continuous symmetry. Any finite rotation can be treated about the same axis, can be treated as product of infinitesimal rotation about the same axis. Okay, so even though I did it for a physical rotation, we have seen from Stern-Gerlach experiment and many of the experimental data that you need to put in another quantum number whose properties are similar, or the angular momentum algebra are similar to what you see for the orbital angular momentum, and we compactly call angular momentum as vector J or operator J in quantum mechanics. So we can try to write unitary operator for a spin J in general particle under rotation by an infinitesimal amount is this. If you want to do the finite rotation about the same axis, the matrices commute. You all know that, right? If I do a rotation about z axis by an angle, let's say 20 degrees, and then do a rotation about z axis by 30 degrees, then it will be like a rotation about the same axis by 50 degrees. Is that right? So they commute. The order really doesn't matter there. So you can try to write the product of unitary matrices for infinitesimal rotation, which you can write it as a finite rotation by n as d theta, and do it n number of times. And this is the formal definition for an exponential function. So there is a unitary operator in quantum mechanics which performs rotation not only in physical space, but it could also be in the spin space or some internal space which we call it as a total angular momentum J, where the generator is the angular momentum J. Okay, so this is what we call it as a rotation operator even in the spin space. So we have been doing this many times, that Jx, Jy, Jz. Now I have tried to motivate you in quantum mechanics even in the abstract space. They can be treated in that abstract space which is like a spin space. Spin half will have a two-dimensional linear vector space. In that space also it is a rotation, and that rotation can be generated by Jx, Jy, Jz, which are generators. And there is one subtlety which you should compare between translations and rotations. In translation, if I do translation along x and then do a translation along y, or if you do y and then x, the final result will be the same, final destination will be the same, right? What is the reason? Generators of the translations, which are px and py, the commutator is 0. But if you do a rotation about x-axis and then a rotation about y-axis and reverse the order, you know they don't commute. Another way of saying is the generators of such a rotation should not commute. So the group of these matrices which don't commute, they are in general called non-abelian group. If you do a rotation about one axis, only one axis, will they commute or no? They will commute. So that is called abelian group. The group of matrices which you write about only one axis will be an abelian group. But if you have three axes, three independent, linearly independent axes, the rotation matrices in general don't commute. The reason for them not commuting is that the generators, which are angular momentum, they don't commute. Okay.